Okay, so first of all, I'm going to look very briefly at some of the UK's carbon dioxide emissions and the role that nuclear power potentially has in reducing those carbon dioxide emissions as a result of the need to reduce emissions because of climate change. That's the key argument that the nuclear industry puts forward to support building new stations in this country. Then I'm going to look in slightly more detail at what our electricity system looks like at the moment, not just generating stations, not just the stations, but also in terms of the broader infrastructure of it. And then you'll notice I'm talking about future energy options, not just future electricity options. What I'd like to see is a situation where we begin to think about how we use energy across the board. In other words, transport, heat provision, and electricity, and not separate them artificially, as we do at the moment. And then, sort of to sum up, just to try and think about some of the implications of building new nuclear power stations and what impacts that might have on one possible future configuration of the energy system in the UK. Okay, so this is looking at the UK's carbon dioxide emissions. As you can see, the top line, the blue line, is our greenhouse gas emissions since 1990. Under Kyoto, we've got a target of reducing those emissions by 12.5% against our 1990 levels by 2008 to 2012. And as you can see, it's not hugely clear, I'm sorry about that, but the light blue line is in fact below the dotted light blue line, which is the Kyoto target level. So in other words, we're pretty much going to meet our obligations under Kyoto to reduce our carbon dioxide emissions. If you look at the lower line, that's our greenhouse gas emissions. If you look at the lower line, that's our carbon dioxide emissions. And the government set itself, when it came into power, an additional challenging target of reducing carbon dioxide emissions by 20% against its 1990 levels by 2010. And when it came into power, it was pretty much on target for doing that. So you can see that there was a sort of a blip in 1996 when carbon dioxide emissions rose, but effectively they'd been on a relatively steep downward incline since 1990. However, over the last couple of years, they've actually started to go up. They leveled off and they started to go up. There's certainly no further decline in the emissions of carbon dioxide. And what that means is that the government set itself a target in 1997. It claims that it's taking climate change very seriously, that it wants to do absolutely everything it can to sort of head off the threats of climate change. But actually, when it comes to the UK's own performance, it's performing pretty badly, and that the government has done almost nothing since 1997 to reduce our carbon dioxide emissions lower from their 1990 levels. What the government also did in 2003 was set itself a pretty ambitious long-term target of reducing our carbon dioxide emissions by 60% by 2050. Very long time frame. Gives you a huge sort of potential to overcome, to sort of turn over all your existing housing stock, to turn over your generating technologies, all of those things. That sort of 50-year timescale should, in theory, be something that you can achieve that sort of major cut just because of the long timescale that you've set. But again, because the carbon dioxide levels emissions have been levelling out, we're not actually making that sort of the progress that's necessary to achieve that long-term target. That's hugely serious for a government that claims that it takes climate change very seriously. Okay, so the nuclear industry, as I said at the beginning, it uses the climate change debate as its major justification for the need to build new nuclear power stations. So this graph, this pie chart rather, shows where we use our energy, what sort of forms it takes. As you can see, petroleum transport fuels is about 47%, gas is about 32%, electricity is only 18% of our final energy use. And of that electricity, that 18% of our final energy use, all of which obviously produces carbon dioxide emissions, nuclear power is only 21% of that 18%. So in other words, only about a fifth of 18%. So in other words, replacing our new nuclear power stations really isn't going to get us very far in reducing carbon dioxide emissions into the future. It's just not actually going to make a huge impact, because effectively nuclear power contributes only about 3.5% of our final energy consumption. So it just doesn't play, unless you're going to expand your nuclear fleet enormously, which is not something that's being proposed. You're not going to contribute anything to reducing the emissions on the scale that is necessary. So what I'm saying is, basically nuclear power, okay, fine, maybe not, it's got a role to play in the future. I personally don't think it has. But actually, if you're talking about reducing carbon dioxide emissions on the scale that is needed and the government is committed to doing, what you need to do is think about the energy system as a whole, not just about electricity. Electricity is 18%. You need to think about all of this, because that's where the majority of carbon dioxide emissions are going to carbon dioxide emission reductions are going to come from. So when I talk about energy systems and electricity systems, I just thought it would be helpful if I explained a bit more about what I was talking about. This is a picture of the UK's electricity transmission network. That's the sort of the pylons that you see sort of dotted around the country, transporting power from the power stations to where it's to more or less to where it's used. And the sort of main characteristics of this system, this network, is that it's highly centralized. That's a sort of term that gets bandied about. I thought it'd be useful if I explained what centralized means a bit. It means there's a very few very large generating systems dotted about, generating stations dotted about on the system. So they all tend to be very large coal, very large nuclear power stations, all of which are sited pretty much away from the areas where the power is actually used. So in other words, for example, down here, I'll show you East Anglia in a bit more detail in a moment. You have the Sizewell nuclear reactor. And actually, most of the power for Sizewell is used in London. It's a long way to ship the power. Long, long way. And the reasons that they're sited remotely, firstly for coal stations, it was because they tended to be sited up here because that's where the coal was. For nuclear stations, they tend to be sited on the coast because they need the water to cool the reactors. But also they need to be quite remote because of the safety concerns attached to nuclear reactors. So you've got a system that's sort of driven by very large stations that are sited in places where ideally you wouldn't put them, because that's not where the power is needed. But, as I was saying, nuclear power sort of effectively epitomizes a very centralized system. Nuclear reactors are huge. They have to be sited remotely. They have to rely on this transmission network, all of these lines, sort of shifting power in very large quantities across the country. At a lower level, what you get is the distribution network. So you have those very large sort of pylon-type things shifting bulk power to and fro across the country. And then once you start getting down to where people actually start using power, that's called the distribution network. Those are the poles rather than the pylons, if you want to think about it that way. This is, as I said, a picture of East Anglia. I tried to get one of the Midlands, but sadly Central Networks, who own your distribution network, they wouldn't let me copy it, so I'm afraid you got East Anglia instead. And one of the key characteristics in a centralized electricity system of the distribution networks is that there's no power stations really sited on these distribution networks. You've got all the lines and you've got people connected to the lines because they want their power, but there's no power stations connected to them because they're all connected to the transmission network. And what distribution networks are designed to do is take the power from the transmission network and ship it one way down the wires to where it's used. So in other words, to your house or to the factory or to your office. Power just flows in that direction. And they're operated passively. In other words, they're designed specifically only to operate in that one-way system. They're not designed to be able to ping power backwards and forwards and sort of act as some sort of balancer. They're just designed to ship power that one way. So I thought it's quite a difficult, if people aren't necessarily familiar with the energy infrastructure, it's quite difficult to sort of visualize what it is I'm talking about. You're sort of guinea pigs here tonight, I'm afraid, because I haven't really tried explaining this in simple terms before. But I thought I'd try and represent it graphically. Here you have the transmission network, the pylons, and that's sort of very high bulk, large amounts of power, bulk power being shipped across the country. And the transmission networks are active. They're allowing two-way flows of power. Lower down the scale, as you can see, the sort of the lines, if you like, get narrower. That's the distribution network, and that goes through decreasing voltages until you sort of end up here, which is where the power is taken off, or most of the power is taken off. At the moment, as I said, a lot of the power stations, whether they're fossil fuel or nuclear, basically inject their power straight into the transmission network. And large users, people who use large quantities of power, very big factories, or actually just very big factories, basically, they can take their power at very high voltage straight off that transmission network. Smaller factories, they take their power off the distribution network, as do sort of office blocks, developments, sort of large local authority projects, whatever. They take they get slightly lower voltage, but basically they're still taking it off the distribution network. And finally, right at the end of the chain, you've got sort of houses, or very small offices, or whatever, so, relatively small users. And in terms of how the power flows on this network, you've got two-way power flows on the transmission networks, and you've got one-way power flows on the distribution networks. In other words, they just take power from the transmission network, and they ship it to the end user. And that's it. That's all they do. They're just there to cart power about in one way, in one direction. And that's it. That's a system we've had in the UK for 50 years. We've increasingly, we've become increasingly centralised, if you like, in the UK. We didn't start off this way, but as power stations got bigger, and as we went down the nuclear path, we increasingly became a centralised electricity system. But that system, I suppose, is being challenged. It's broke. It's we know that it's a problem in terms of carbon dioxide emissions, and to a large extent also in terms of nuclear waste. But we know there are big environmental problems with this system. And there is a new context about talking about the electricity system and the energy system generally. You've got a political consensus that has been fairly robust for the last 15 years on climate change. You're not going to get any significant UK politicians saying they don't think that we don't need to act on climate change. You've also got a growing amount of public concern on carbon dioxide and the need to reduce emissions. People are becoming increasingly aware of the personal role that they play in how much energy they use, what their carbon dioxide emissions are, and what the implications are, both for themselves and for future generations. And part of this new context, which I think is really interesting, and I want to look at it more in my research, is that actually you're getting to a situation now where people are physically going out and protesting against fossil fuel stations. These are pictures taken from Drax and Didcot, two large coal stations. That's something that's never happened before in this country. People have protested against nuclear power stations for years. Nobody's ever batted an eyelid about coal stations before. In the last couple of years, people have actually got up and said, we don't want any more coal stations. It's a very interesting new public debate going on. The bottom picture is what happened. It was a huge sort of protest that took place at the end of last year, I think, in Trafalgar Square, where there were sort of tens of thousands of people saying that they wanted action on climate change and carbon dioxide emissions. So it's an interesting new debate that politicians have yet got to take on board, I think, really. So those are sort of the environmental issues. In terms of security issues, if you like, security of supply, how happy you are that you're always going to get power and to be able to switch on your light bulb when you want to switch on your light bulb. Firstly, energy prices are rising. And that's not in itself a security problem in the sense that, that doesn't actually mean that you're not going to be able to switch on your light bulb. What it may mean is that you may think twice about switching on your light bulb because you don't want to have to cough up the extra money to pay the energy companies for the power you're using. So in that sense, you're slightly less secure these days about energy. People are much more engaged in thinking about how much they're spending on power. We also got a situation where we've used up a lot of our natural gas, and we're increasingly going to become reliant. If we continue down this sort of gas, fossil fuel, nuclear route, we're going to become increasingly reliant on importing gas, whether it's from Eastern Europe or North Africa or anywhere else. We are going to be a situation which we haven't been in for a long time in this country, where we're reliant on energy imports. Also, the infrastructure is getting pretty old. The pylons and the distribution line poles, they were designed for 40 years. 40 to 50 years is their lifetime. And most of them now are reaching the end of that lifetime. They're going to have to be renewed. And that's something that's going to cost billions of pounds. And will have to be spent over the next 10 to 15 years. So we need to start spending money on our energy infrastructure. If we don't do it, then the lights are going to start going out, firstly. But secondly, more importantly from my point of view, spending that money, the need to renew our energy infrastructure also gives us an opportunity to change it rather than just replace it. And then there's sort of broader security concerns about sort of terrorism, the possibility of attack, not just on nuclear power stations where there's been quite a high profile debate about security issues, but also on other stations and other parts of the infrastructure where there is a possibility, there's sort of scenarios people have put forward, for example, of people bombing transmission networks and effectively cascading power failures down the system because it's so centralized, because everything relies on the transmission networks to ship power around the country. That's something that's a very real concern. So what you've got there is a set of environmental and security drivers for the energy policy debate, which are effectively new, haven't really been high profile so far. But what it does mean is that there is a possibility at the moment to challenge the current model of the UK's electricity system, and to think again about how we decide to configure it, what we decide to use to generate our power. And what the system looks like. And I'll just give you a quick outline of what I think a future system could look like in this country. You've basically got the same deal. You've got the transmission networks, you've got the distribution networks, you've got the big power users, smaller power users, finally getting down to houses and people. Effectively, you've got the same infrastructure, more or less, and you've got the same set of users. But what in this different system you could have is would also have power coming into the transmission networks, although it'd be much lower levels than it'd be much smaller amounts of power than there are currently, and there would be a much more diverse set of power generating options. So you could have wind, you could have wave, you could have some fossil fuel. Why not? But it would be relatively small amounts of power. And instead, you would have power based on the distribution lines. And that would be largely renewable power. So wave, wind, solar power, either solar thermal or PV, and also biomass power. And that would be injected into what have previously been passive distribution lines, making them an active participant in the electricity system. In addition, there are a whole pile of new technologies that are coming forward at the moment to store energy. Basically, these are meant to be batteries, not nuclear waste barrels, which I realized they looked like earlier. Part of the problem with renewables, and one of the problems that renewable sort of skeptics highlight, is the fact that a lot of it generates intermittently. In other words, it's not constant. You don't get power coming out of your windmill if there's no wind blowing. But what you can do, and what increasingly looks like it's becoming increasingly economically viable, is to store that power. So effectively like recharging a battery. So that when there's an excess of wind, you take the power, you store it in your battery. When the wind's not blowing or when there's high demand, you pump that power back into the grid. And obviously, that would be a way of counteracting this problem of intermittency with renewables. In addition, you could have sort of combined heat and power plants. In other words, plants that generate both electricity and heat, and the heat's used by either small factories or large offices or whatever. So they'd have a little power plant in their basement where generating electricity, plus also using the heat, or using the heat to power sort of fridges and things, because that's a whole other dimension, this sort of using combined heat and power plants to actually produce air conditioning. Don't ask me how that works, it's beyond me, that one. But they, in addition to sort of taking power off the grid, they'd also be in a position to inject power into the grid. And finally, you would have some houses, all houses, housing developments, whatever, also producing their own power. Each house, we've heard a lot about, David Cameron's little wind turbine, his micro turbine. But increasingly, there is a lot of attention from local authorities and planning developers on the potential for larger scale development-wide renewable projects, whether they're combined heat and power or whether they're solar or wind power. And that doesn't necessarily just have to produce power for that development. It can also export the power back onto the grid. And obviously, if you've got a turbine on your house that's exporting power to the grid, that you're going to get payment for it. So there's an economic argument to, which is why developers are increasingly interested in it. So the key fundamental difference I wanted to highlight between this system configuration and the one I talked about earlier was, again, you've got two-way power flow on the transmission network, but because you're having power injected into the distribution network, that's also designed to allow two-way flows of power. And it's become an active participant in the electricity system rather than this sort of passive recipient of power from the transmission grid. Okay, so I hope, is that all clear? Does everybody understand all of that? Does that make sense? Okay, all right. This is the guinea pig bit that I haven't tried out on anybody before. In terms of the differences, so the fundamental differences between the centralized and the decentralized models, and climate change stuff, you've still got a high reliance effectively on large-scale fossil fuel stations, whether that's coal or gas, because you still need centralized generation. In a decentralized system, you've got increased use of renewables and a higher degree of energy efficiency, or efficiency of the system, because the whole system is active. You're losing less power through shipping it long distances. It's a more efficient system. So overall, you get lower carbon dioxide emissions. A broader environmental issue, you don't have the sort of issue of nuclear waste and accidents that you would have in a centralized model with nuclear power. On a security level, you remember I talked about all these issues about a reliance on imports and the potential for terrorism. A centralized model, because it would still be using gas and nuclear, you would still rely on importing your primary fuels. Whereas in a decentralized system, which is based on renewables, in other words, the wind or the wave or the solar power that we have already, you would be much less reliant on imports. You'd be using instead our own indigenous fuels. Again, on security and this terrorism question, you have got this vulnerability to attack either of a station or of the network itself in a centralized system. And the decentralized one is less vulnerable because it's more dispersed and it's lower level. And actually, it doesn't matter quite so much if you blow up the transmission line, because actually, most people are getting their power from the distribution network anyway. In terms of efficiency, I touched on this a bit earlier. When you're shipping power long distances over the transmission network and then down through the distribution networks in this sort of centralized one-way model, you lose a lot of the power just because of the distances you transmit it. So if you're transmitting it less far because you've got a power station a lot closer to you, you've lost a lot less of the power. So in that sense, it's more efficient. But in a broader system issue, and this is a key sort of difference between the centralized and the decentralized models. When most power stations, whether they're nuclear or fossil fuel at the moment, they don't use the heat that's produced by burning. A lot of the heat is lost. Whereas within a decentralized model, you'd actually, because it's close to people's houses, for example, you'd be able to take the heat and use it for your central heating or whatever. You're actually physically using the heat that's the waste byproduct of most power stations at the moment. So it's much more of a system, if you like. Going back to those pie charts, you're actually not just addressing electricity. You're also addressing some of the gas use as well and some of the petroleum use. So you're thinking about, you're getting much more of a system solution to this. In terms of cost, which obviously is a key political issue as well as something that affects all of us. Under a centralized model, because you've still got a lot of fossil fuels, you would have increased, over time, you'd have higher levels of carbon dioxide emissions and therefore increased climate change impacts. In terms of cost, the difference between the costs of the centralized and the decentralized models, I think that's a difficult one to say at the moment. I don't think anybody actually knows at the moment what it would cost to build new nuclear power stations in this country. Certainly the government doesn't. But then again, nobody actually knows what these new technologies are going to cost either. The only difference is that we've had 50 years of nuclear power and actually the costs have gone up rather than gone down. Whereas a lot of these new technologies, wind, wave, solar, whatever, their costs, although they're still high, relatively speaking, compared with gas, they are falling. They haven't sort of shown this the problems of ever increasing costs that the nuclear industry has. So I think if you're taking a bet, I would go for the smaller scale, less. More novel technologies at the moment than I would to put my reliance in nuclear power and it being a cheap future generating option. And then there's other issues which may or may not be interesting. One of which is that in a centralized model, as I was talking, all the power stations are sited way away from where you live. You don't see nuclear power stations. If somebody, unless you live next door to them, you don't know where your power comes from. In a decentralized model, you would know pretty much where your power came from. It may come from your own roof, who knows? But that gives you not just you yourselves become part of this system, and because you're part of it, you've got a greater degree of control over it, and that that sort of level of responsibility should in itself lead to greater awareness and lower carbon dioxide emissions on an individual level. Okay, so. When I started off, I said that the government's thinking about building new nuclear power stations, and I wanted to think about what some of the implications of that decision would be in terms of the sort of future configuration of the energy system, not just the electricity system. And I think one of the things my starting point, in a sense, is that the two things are effectively incompatible. You're talking about building nuclear power stations that cost billions of pounds. Each individual station costs billions of pounds. Or you're talking about putting billions of pounds into lots of little things. Either way, you're talking about billions of pounds, but there's a huge difference between the two. They're not, you can't really balance them up. They're sort of incommensurate, if you like. Either you spend billions of pounds on a few very big stations, or you spend billions of pounds on a new energy system based around lots of little stations. And if we think about the history of the nuclear power industry in this country, it's had a huge institutional commitment, up to when they privatized the electricity industry in 1990. Um, until then, which was the first time sort of the economic problems of the industry were exposed. Until then, there was a huge amount of government and political support for the industry. And that's not just in terms of politicians running around saying, we like nuclear power stations. It's in terms of them actually physically giving the industry millions of pounds for research and development, or making sure that there's dozens of people within the Department of Trade and Industry to look after all the administrative problems that the industry has, all the licensing issues, all the licenses that they require. I mean, it's difficult to underestimate the importance of the importance of that level of institutional commitment. If you think about it now, at the moment, because the government's thinking about building new nuclear power stations, you have dozens of people working in the DTI at the moment, either directly or indirectly, looking at licensing, looking at pushing through the consultation process, looking at, I don't know, working out what the economics of nuclear waste disposal are going to be. All of those things. There are dozens of people within the DTI, a whole unit looking after this. And in contrast, you've got one person looking after all of the government's microgeneration strategy. In other words, one of the key what it says is one of its key strategic long-term aims, getting little windmills on people's houses, all of those things. You've got one person doing it compared with dozens for something that they are not meant to have yet, to support a program they're not yet meant to have started. I mean, that's sort of the level of difference in terms of that institutional support. And that is, that's something that will, in the long term, damage the renewables industry. At the moment also, you've got a market, an electricity market, that's designed to support the centralized model. In other words, small-scale, decentralized power and power station operators, they find it very difficult to sell their power. And they find it very difficult to get a decent price for their power, because the whole market and the whole way electricity is traded is geared towards having great big bulk amounts of power traded one way or the other. And that's a sort of an institutional framework that just means that sort of smaller scale options are effectively excluded from being economically viable. And then there's a third issue that I think needs highlighting, which is if you're going to decide to build 10 great big new nuclear power stations, or 5 great big new nuclear power stations, or whatever, that sort of means that you're sitting back thinking, well, we don't need loads of windmills, and we don't need a lot of, to put a lot of resources into developing our wave power expertise, for example, because we've got, great big new nuclear power stations coming online. So we don't need any more power. And that's a situation that's already seems to be happening in Finland, where they're building a new nuclear reactor. It's the only reactor that's being built at the moment in Europe. It's a place called Olkiluoto. And what's happened is, since the government made the commitment in Finland to build this reactor, carbon dioxide emissions have gone up in Finland, because everybody's assuming that they'll be able to meet their Kyoto targets when Olkiluoto comes online, because it's a great big lump of power that will be carbon free. So what they're basically saying is, we don't have to do anything to reduce our emissions till 2008, because that's when the power station will come online and our emissions will drop automatically, so we don't have to worry about it. And in the interim, their emissions are going up. And at the same time, because there's a great big lump of power coming online, people aren't putting money into renewables and energy efficiency because they're scared that there won't be any need for the power, they won't be able to sell it. And the other issue with Olkiluoto, which is something that's inherent in any nuclear project, is that it's already delayed. They've been building this station for about a year, about 18 months, and it's already 18 months behind schedule. In other words, they might as well not have bothered starting. They've got huge technical problems with this, but they're also pouring in huge amounts of resources, and people are getting very complacent in the interim about their carbon dioxide emissions. So does all this matter? What I'm basically saying is, if you're going to build new nuclear power stations, you're not really going to be able to have a decentralized energy system. It's just not going to be worth it. You're not going to have lots of renewables. You've got to make a decision between one and the other. And in policy terms, regardless of my own personal view, in policy terms, there is a key issue that politicians need to think about in terms of carbon dioxide and what the nightmare scenario, if you like, is, which is that they decide to commit to a nuclear power program. They build, they say we're going to build 5 stations or whatever. And in the interim, as happening in Finland, you stall investment in renewables, in CHP, and nobody bothers trying to reduce their demand because they think, well, we're going to get loads of carbon-free electricity in the future. And then, for one reason or another, you don't get your nuclear program in place on time, as already seems to be happening in Finland. But the UK's record of building nuclear power stations is pretty appalling. We can't do large-scale infrastructure projects in this country, as we all know, and they inevitably, all of the nuclear power stations that have been built in this country have been delayed and have been well over budget. And we've had nuclear programs in the past. The most recent one was in the early 90s when we were going to build, I think it was 6 nuclear reactors, PWR reactors. And in the end, we only ended up with 1, which was at Sizewell B. We don't achieve our nuclear programs anyway. So you don't get what you wanted, but in the interim, you've damaged the development of renewables and CHP, and as a result, you end up with rising CO2 emissions. So that's the political danger, the environmental danger of going down this route. Okay, so I think that's pretty much all I wanted to cover. I think it's quite a sort of complicated set of things to get your head around. So, but just to sort of recap a bit, nuclear power doesn't really have a huge role to play in the UK's carbon dioxide emissions as such. It's about 3.5% if you have a replacement programme. And given that, actually what we need to do is, instead of having a debate about generating options, in other words, nuclear power versus renewables, what we actually need to do is have a debate about what our future energy system will look like and how nuclear power may affect the development of that future energy system. And basically what I would argue, on the grounds of their sort of environmental performance and also in terms of how secure the energy systems are, I would say that there are better options for a future energy system than trying to build new nuclear power stations at the moment. What we need is something much more decentralised, much closer to the people, and much more based on renewables and demand reduction. So thank you very much. That's it. That's it.
Does anybody have any questions for Bridget? Yes, please.
Could you bring up the original pie chart? So we've got
The pie chart, yeah. Sorry. Oh God, I don't know how to do it. It won't let me do that. Oh, we go. That one. That one.
I mean, this isn't, I'm not arguing for this particularly, but you were saying that, you can only do that sort of 18% because that's the electricity that's generated, but can potentially houses be heated using electricity and potentially sort of electric cars as well, which means that it could have a much bigger chunk of the sort of amount of power.
No, that's true. That's true. I mean, I think in order to, for example, get a lot of you would, if you're talking about expanding the electricity sector to have an electricity sector that's much more based on nuclear, then you're looking at a huge program of nuclear reactors in order to be able to address sort of electric heating and electric cars. So you're looking at something like the French program, where they've got 75% nuclear electricity generation, and quite a lot of that is directed towards house heating and things. And I don't think anybody's particularly talking about having a nuclear program on that sort of scale. I think I think the UK pretty much would rule that out. And the other thing, I mean, yeah, I think that you'd find it quite difficult to operate an electricity system in this country that's based on, sort of a very high proportion of nuclear power. One of the things that I didn't talk about, but nuclear power stations can only operate at full output, if you like. They're all or nothing. Yeah, they're either full output or they're shut down. Whereas if you think about how demand works during the day, you obviously first thing in the morning there's very high demand. At 5 o'clock in the night, 5 a.m. there's no demand at all. So demand goes up and down like that. And if you've got a lot of nuclear power, actually, it can't cope with the fact that demand's going up and down and spiking like that. And the reason the French can do it is because at night, firstly, they've got very high degrees of electricity heating, but also they export their power very cheaply at night to the rest of Europe. Whereas the UK, because it's an island, is you're not hugely interconnected with the rest of Europe in terms of electricity system. So it would really suffer. It would find it very difficult to cope with that sort of a high level of nuclear output plus demand going up and down. So technically speaking, they'd find operating a system with that sort of level of nuclear output very difficult. Yeah, they could. Yeah, I mean, and they have done. I mean, they've got this big lake up in Wales whose name I can never remember, which is pumped storage, which is used at night. It sort of pumps water up the hill because power's cheap. And then, sort of in the day when power's expensive because there's a high level of demand, it's used to generate power.
It's only used for cup files and all that.
Oh, when everybody makes a cup of tea. No, it's tiny. But I mean, they do use storage, and there is that sort of storage facility. Yeah. I mean, they could do, yes, but I mean, even then, it's a big infrastructure thing. That I mean, it's that sort of level of storage. Or you could build more interconnectors to Europe, I suppose. But I think, I sort of prefer a much more decentralized option. I think it would be simpler.
Yes, first of all, thank you very much for a really fascinating talk. Thank you very much. I'm going to declare an interest. I've spent about 2/3 of my working life involved with coal-fired power stations, about 1/3 with nuclear power stations. So I do see both sides of this. And I agree that we mustn't see electricity on its own. It was so right to put it in the context of the total energy scheme. But picking up the earlier point, I do think if you look far enough into the future, you do start to see a lot more transport being electric-based. I think if you go far enough, you can actually postulate a hydrogen economy where the whole thing is can be electricity-based. So I think it is important to focus on the electricity. What you do about air transport, I'm not too certain, just at this moment in time. Just a few points, and I'm not being pro-nuclear or anti-nuclear, as I say, I've seen both sides. But some of the comments you made were perhaps a little bit simplistic, and they have to be when you're covering such a huge spectrum. But the nuclear plants can load follow to a significant extent.
Not.
Let's have a technical debate.
Okay, that's not. I mean, they're not designed to.
I would suggest that they can, in some parts of the world, have to and do.
Okay, I'd differ from that for two reasons. Firstly, they can. I mean, in theory, they can.
Yeah.
But there's two reasons that they don't. One is that technically, sort of the increase and decrease of temperatures that is implied with load following. It makes it is very stressful for the reactor, and they don't like doing it for technical reasons. The second reason is that economically, they have to operate at full output in order to be able to pay back the huge amounts of money that they've spent building the reactor in the first place. So they don't like it for economic reasons either. So I mean, they can in theory, but they don't.
Yeah. That just leads you to a sort of maximum percentage level of nuclear generation on the system. But the question I really wanted to work my way around, because I've been a long time. In your model of
Mm-hmm.
And I do agree with you that the trends are going in that direction. But we still have to, first of all, go for energy efficiency and energy savings as much as
Yeah.
we possibly can. That's always at the top of my list. But then we've got to balance, apart from things like pumped storage and big battery devices, we've got to balance generation with demand.
Mm.
And if we don't get a significant net reduction in gross demand, the generation will be met from somewhere.
Mm.
Now, on that drawing, we've got all those renewables, and I support them. But what is your view on a on a maximum percentage of total electricity generation in this country coming from renewables to give us any sort of security when you have things like anti-cyclones, no wind, no wave? You've got biomass, yes. We've got a little bit of storage, maybe, but not a great deal. Even the Kraken and Transfinid.
No, that's what it's called. Yeah.
Transfinid, yes.
The Transfinid's the nuclear station, isn't it?
300 megawatts it is. What is your view of the percentage you could probably meet by renewables, even in a distributed system?
Okay.
Security.
Yeah, no, I think that's an interesting question. I think that you could, in theory, have a system that is entirely based on renewables, but it depends on the mixture of renewables you have. So you could have some wind and some wave, but as you've said, they are intermittent and subject to weather patterns. Tidal isn't. It's intermittent, but it's very predictable.
Yes.
So you can sort of compensate. The more different technologies you've got, the less impact all of that intermittency has. If you have a high degree of biomass, a potential for demand reduction, not just energy efficiency, so people voluntarily going offline or for whatever reason, and a degree of storage, quite a high degree of storage, I think, then you could, in theory, have a system that's entirely based on renewables. Whether or not I think that will happen is a different thing, and I don't think it will. I think there will always be a reasonable quantity of gas on the system, and that's the cheapest option at the moment. And the question then is how you use that gas most efficiently, and that's got to be, okay, if you're going to use gas, and there are security advantages for using gas, then make damn sure you use the heat as well. Don't just use the gas for a generation. And that's a huge mistake we made over the last 20 years. So we built a lot of, well, the last 15 years, we built a lot of gas stations, a lot of new gas stations in this country, which only generate electricity. All the heat is lost. And actually, we should have built them to produce heat as well. And we wouldn't be nearly so worried now about what our carbon dioxide emissions are.
You mentioned Finland making a bit of a mess of it. Is there a country that you would point to that actually is doing the opposite?
Well, I'm glad you asked me that. As, I didn't know how long this talk was going to take, and I didn't know quite how detailed the audience wanted me to go into it. This is a picture of the UK's energy system in sort of conceptual terms. You've got your inputs here. You've got, so for example, you've got all the gas and the coal and things going into the power stations here. I don't know how clear it is, I'm sorry. This is power stations anyway. And then you've got your outputs here, total final consumption. And all this stuff down here, coming from the power stations going all the way down there, that's system losses. So you put all that power in, and that's what you can work out pretty much what you get at the end of it. It's all the orange stuff. Oh, is it orange? No, it's red. It's orange on my screen. All that stuff is all the power that's lost, all the energy that's lost in the UK system. So those are power stations, those are your losses. And you input into this system 87 units, million tons of oil equivalent in this case. Power stations of final end use is 29 units. In other words, 60% of our power, one way or the other, is lost. 60% of our energy through this sort of power station system that we have at the moment. And this brings me to your question, which is, this is the Danish system. Same deal. These are the power stations. They do it slightly differently, but these are the power stations here. And these are the losses there. And in this system, in the Danish system, you get 415 units put in. They use a different unit of measurement, the petajoule. And your output is around 200, your end use is around 278 units. So in other words, you have losses of 33%, half of what you get in the UK in terms of efficiency, twice as efficient. And the reason they're twice as efficient is, firstly, they've got a lot of CHP, a lot of combined heat and power stations, which are small stations that are located down the bottom of your road. They're not miles away. So you get less losses, you're more efficient, you get lower carbon dioxide emissions. And another issue that is particularly significant with the Danish thing, although not so much in this context, is that they also have very high levels of use of wind. They have about 20% of wind on their system, compared with about 2% in the UK. So yes, there are countries that are doing it better than us, one of which is Denmark. It will blow Denmark away, actually. It was
These small local ones you've got there, what's the power, the input power of that? Are they gas or?
Some of it's gas, some of it's biomass, so some of it's plant material. It's a mixture. And I think also some of the older ones are coal. I mean, the other thing about the Danish system, it's not ideal. I mean, there's quite a high degree of coal use in the system, but they use it more efficiently. They don't waste it so much. So yeah, it's gas, coal, or biomass.